Hi everyone, I'm Manas. I'm TA for CSE 251A, and today I'm gonna talk about Perceptron and support vector machine. So here we're gonna talk. It's going to be a little bit shorter discussion. We'll just learn what is Perceptron. We'll see how to train a Perceptron, and then we'll just start with the support vector machine to see what are the common terms related to support vector machine and why do we need it. So let's get started. So first of all, what is perceptron? Well, to put it simply, it's just a binary classifier. As you can see from the image here, like we have two different classes for our 2D data. So what perceptron does it just creates the decision boundary to separate these two data. And what does our decision boundary looks like? So decision boundary in perceptron is given by wx plus b is equals to 0, where w is the weight vector and b is the bias term. Both w and b are learned. So b is a scalar value and w is our same dimension as data. So in this case, the weight vector is a 2D and b is like just a scalar value as our data is two-dimensional data. So now how we use this decision boundary to predict the classes? Well, we just put the data in the equation wx plus b, and if the output is positive, then we predict class A or generally like +1. If the value is negative, then we predict the data belongs to class B or -1. So, and what does a decision boundary looks like? Well, if your data is a single dimensional data, then like that means it lies on number 9. Then it's just a point. Let's say your data is spread from like 1 to 10, then that point can lie any between 1 to 10. Let's call it theta. So all the values that are greater than theta are belongs to class A, and all the values less than theta belongs to class B. Similarly, for a 2D data, the decision boundary is aligned. For n-dimensional higher level data, the decision boundary is just hyperplane. So what's the difference between a perceptron and linear regression? Because this does look a lot like linear regression. Well, it's basically the same thing, only in case of perceptron, we add these binary thresholding at end. If we remove this binary thresholding, then it's same as linear regression. All right, now let's see how to train a perceptron. All right, for this case, we'll just assume our labels are +1, -1 instead of dealing with class A and B. So as does this sentence make sense? That our prediction is correct if y into wx plus b is greater than 0. So there are two cases to that. If y belongs to the +1 class, then if we predicted that using wx plus b that it belong to +1 class, then this value would be positive and this value would be positive. And positive into positive will be greater than 0. So our prediction would be correct. If y was incorrect, and then if y was belongs to class -1, and if we also predict that it belongs to class -1, that means wx plus b is less than 0. So even minus negative into negative will be greater than 0. So in general, we can say if y into wx plus b is greater than 0, then our prediction is correct. If it's less than 0, then our prediction is false, right? So using this, we can define our loss function as if our prediction is 0, then our loss is 0. If our prediction is incorrect, then our loss is just negative of this multiplication value. Okay. So if we are far off, like if y was like -1 and we predicted it to be in +1 category, we'll get loss as a negative of negative, which is like finally a positive value. Okay. We want to minimize this loss. Right. Now we'll go through a Python notebook to see how do we train a perceptron. Okay. All right, we just start with some normal library imports. We'll use get points on boundary as a helper function to just plot the decision boundary at the end. So right now we don't need to do anything with it. So let's just start generating our data set. So our data set, for us to visualize it easily, we're just having a 2D data and we'll have like 100 points, okay? So 50 would be of class +1, 50 would be class -1. All right, let's just visualize what this data looks like. So this is our data, one in color blue, one in orange. As we can easily see, there are a lot of decision boundaries that we can learn, which will separate this data easily. So let's try it and train a perceptron to do it. So this is our perceptron algorithm. What is it? We initialize our weight vector unbiased to 0. We cycle through our training set, and whenever we are predicting wrong, we update the base weights and bias. Like whenever we misclassify training data X, Y, we update weights and bias corresponding for that data. All right. So let's see the Python code for it. Again, pretty straightforward. We initialize W to 0, same dimension as our data, a bias also to 0. All right. So okay, we need to now cycle through training data. So we're just going through data, and if we are predicting wrong, if W into X plus B is less than 0, less than equal to 0, then we update the weights correspondingly. So we update weights and we update the bias, and we keep on doing it until we converge. So that's what this outer loop is for. It just checks like if anywhere we are going wrong, it just keeps on iterating. Okay, so we try doing the same steps until and unless we converge. And for perceptron, it is guaranteed to converge if the data is separable. Okay, so this will always converge. However, we do have a max limit here. So if it's taking too much time, then we just stop. Okay, like it might lead. Yeah, we'll see when that happens. So we just train it, and I'm just printing W and B. So this is the weights vector I got, and this is the bias I got. So let's just plot this decision boundary Wx plus B on our data. So yeah, we see like a decision boundary that we got using training the our perceptron did segregate both of these classes such that all the negative class lies below it and all the positive class lies above it. Okay, and there are no misclassifications. Okay. Let's do one other thing. We'll try to train perceptron again and see if we always get the same boundary or not. All right. But this time what we'll do is we were just cycling through training data, right? We'll just shuffle the order of data. So here we just randomly shuffle the order of data and just use the same training procedure again. Okay. So we saw again, we got this time a slightly different decision boundary, right? But even this decision boundary was able to segregate both the classes, if you'll see. So here it was like negative 2.71 and 1.2. And there it was negative 2.56 and 1.8, right? So we have like multiple decision boundaries that were able to segregate this data. Okay. Now let's go back and see what we learned. Yeah, all right, we did that. All right, so we'll see what all we learned. First of all, for perceptron learning, the convergence is guaranteed if data is separable. So if we get a data of this in which decision boundary exists that can 100% segregate the data, it will happen. If the data is not separable, then the convergence will not happen. Okay. Secondly, time taken to convert depends on sampling of training data. So basically, we sample training data in a random order, right? Now, it kind of depends on our luck, like how fast or how slowly we converge. Just depends on that random ordering, right? And third thing that we learned was multiple decision boundaries are possible for the same data. Okay, so as like for the figure given here, one of the decision boundary can be like this, another can be like this, another can be like this, and one more can be like this. I think there are like infinitely many decision boundaries possible. However, just intuitively, we know some decision boundaries are better than others, right? Like, you know, even though this purple decision boundary makes sense for this data, we know a decision boundary that lies in the middle will be able to generalize better for the testing data, right? So we would much rather prefer this red decision boundary than this purple or this violet decision boundary, right? Now, to just solve this problem, we have support vector machines. So let's see what SVM does. All right. So what does support vector machine does? So there are multiple decision boundaries possible, right? For the data that's given here, one of the decision boundary that separates the data is this blue line. One of the data that separates this, one of the decision boundary that separates this data is the red line. However, we would much rather prefer red than the blue line, right? And support vector machine just helps us to do that. How it does that? So it just tries to maximize the margin between the decision boundary that we have and the nearest points from this margin. Okay, so in this blue case, the nearest point was this and this for class +1 and minus. And for the red, we have nearest boundary as this nearest point as this guy and this guy for this red. So what SVM does is try to maximize that distance. So we'll much prefer have H3 boundary than H2, and H1 is not a decision boundary at all because it doesn't even segregate the data properly. All right. So the aim of support vector machine is to maximize the margin. Margin is just the distance to this nearest point. Okay, that's the aim of support vector machine. And yeah, and the nearest point to a decision boundary is called support vector. So for H3, the support vector is this point and this point. For H2, support vector is this point and this point. And these are the only points that define how this decision boundary will go. So if you have techniques like linear regression or like some feed-forward neural network, in their decision boundary depends on all of the data, all right? But support vector machine is unique in that kind of way, in which your decision boundary just depends on your support vectors. And what are support vectors? It's like the closest point of a class from the decision boundary. I guess, yep, this is it. It was a bit of a short discussion. However, if you guys have any doubts, please feel free to reach me out on Baza or email. Thank you.